The applications of scientific notation are going to allow us to work through several problems where we actually use scientific notation to solve them. So we're going to work through these 11 problems, and feel free to try them on your own and then come back and watch how they're done. And there are a couple different ways that you could do some of these, so don't be worried if you kind of go about it maybe a little bit differently. So number 1, suppose a particular state has $31 billion budgeted for K through 12 schools. If that money is dispersed among 292 school districts throughout the state, how much will each school district receive? Well, one of the big questions is, do I add, subtract, multiply, or divide? How do you know what to do? Well, in this case, we are dispersing money, right? We are splitting it up evenly. So if I'm splitting it up, right, I'm divvying it out to the different school districts, I'm dividing. So I'm going to take the money and divide it by the schools. So I've got 31 billion over 292. All right, well, 31 billion. Recall that billion means to the ninth. And I know that 31 times 10 to the ninth is not scientific notation, but we're going to leave it like that for right now anyway. Now, 292, if I make that scientific notation, that's a 2. Now I have a problem that I can do. So even though 31 is not in scientific notation, I can still divide that. 31 divided by 2.92 gives me 10.616. Times 10 to the, I subtract my exponents, 9 minus 2 is 7. Now, we don't talk about money in terms of scientific notation, so I'm going to change this back to standard form. 7 places. So I start here, 1, 2, 3, 4, 5, 6, 7, right? The end is just zeros. Throw in my commas, and each school is going to get roughly $106,160,000 for each school. Number 2, it is estimated that a single droplet of sneeze can contain as many as 200 million germs. All right, so 200 million in one drop. A sneeze has 40,000 drops. So each one of these drops has 200 million germs. So now I'm not divvying it up. I'm trying to get this. I have 1. What happens if I have 40,000? So now our number is just getting super big. So I'm going to take 200 million times 40,000. All right, well, let's look at this in scientific notation. Remember that million means times 10 to the 6th. And if I take 200 and move it 2 places, that means this is going to get bigger by 2. So 200 million is 2 times 10 to the 8th, right? Million is 6. Then I moved this 2 places to get the 8. Times 1, 2, 3, 4, 4 times 10 to the 4th. Okay, and if you're having trouble with that, you might want to go back and just watch another scientific notation video to recall how to go back and forth between standard and scientific. And now we multiply. 2 times 4 is 8, and we add 8 plus 4 is 12. So times 10 to the 12th. Now, times 10 to the 12th, this number implies trillion. So this is the same as 8 trillion. So a single sneeze can contain up to 8 trillion germs. I don't know about you, but that's a lot of germs. Number 3, according to their website, Lucas Oil Stadium holds approximately 70,000 spectators. How many stadiums would it take to hold the entire U.S. population, which is approximately 324 million people from a previous section? Okay, so now think of this. We're trying to figure out how many stadiums. So we're taking the U.S. population, 324 million people, and we're going to divvy them up into different stadiums. So as soon as you start splitting people up, you're dividing. So people divided by stadiums. So we know that we have 324 million people, and we have 70,000 spectators. So let's go ahead and put these in scientific notation. Again, million means 6, but if I move this 2 places, that gives me 3.24 times 10 to the 8th, because here's 6, 7, 8. That's how I got the 8. Divide this by 1, 2, 3, 4, 7 times 10 to the 4th. Okay, so now when I divide, right? I divide my first numbers. 3.24 divided by 7 gives me 0.46287. I took it out quite a bit. Times 10 to the 8 minus 4 is 4. We're not going to say, well, 0.46 times 10 to the 4th stadiums. Doesn't make any sense. So if I move my spot 1, 2, 3, 4 places, 4628.5, 5 rounds up, so let's round that to 4629 stadiums. So it would take 4,629 stadiums, Lucas Oil stadiums, to fit the entire U.S. population. Number 4, recently a meme on social media was divvying up lottery winners. Okay, there you go, you're divvying it up, so we're dividing. If the jackpot was $1.3 billion, and the meme estimated a population of 300 million people, how much would each person win? All right, so let's look at this. And I remember this when it was on social media. So we've got 1.3 billion divided by 300 million. Okay, let's go to scientific notation. Billion means 9. 1.3 times 10 to the 9th. Okay, now million, we know million means 6. But to move our 300, 6, 7, 8. So 3 times 10 to the 8th. Now, if I divide 1.3 divided by 3, so here I get 0.433 times 10 to the 9 minus 8 is 1. Let's move this back to standard form to talk money. One place, so boom, each person is going to win $4.33. Dude, I can't even eat at McDonald's for $4.33 these days. So it's not really going to work to split that 1.3 billion to the entire U.S. population. Number 5, using scientific notation and the product quotient rules, answer the following. How many hundreds are in 1,000? Okay, now if you think about this, we're trying to figure out how many of these we can fit inside the other. So if I start with 1,000, how many hundreds can I fit in that? Well, that's division, right? You're trying to take the 100s and fit them. How many can you fit nicely in there? So if I want to change these to scientific notation, 1,000 is 1 times 10 to the 3rd. 100 is 1 times 10 to the 2nd. Dividing by 1 is easy. I end up with 1 times 10 to the 1st. And if you change that to standard form, right, we move our decimal 1 place over, we just have 10. So there are 10 hundreds in 1,000. Okay, letter B. How many 1,000s are in 100? So now we flipped it. We start with 100. How many 1,000s do we have? Well, now we have 1 times 10 to the 2nd over 1 times 10 to the 3rd. And that leaves us with 1 times 10 to the -1. Because 2 minus 3 is -1. A negative exponent tells you to take your decimal and move it the other direction. So my decimal is now going to be over here. I'm at 0.1. So there is 1/10 of a 1,000 in 100, which makes sense. If we move our decimal, boom, there is where our 100 comes from. Now, what does a negative power of 10 mean? Well, a negative power means you move to the left. So you move left, your number gets smaller. If you have a negative exponent, it means a small number. When I talk small numbers in scientific notation, we're talking less than 1. Okay, so negative exponents less than 1. And if you have a positive exponent, right, like these numbers up here, positive exponent means bigger than 10. Because remember, scientific notation is between 1 and 10. So small number means less than 1, big number, bigger than 10. All right, let's go to 6. Same concept. How many millions are in a trillion? Well, that means we're going to put the 1 trillion on the top and the 1 million on the bottom. Trillion is 1 times 10 to the 12th. Million is 1 times 10 to the 6th. So scientific notation, using the quotient rule, 1 times 10 to the 6th. Well, 10 to the 6th is million. So there are 1 million millions in a trillion. And you might be thinking, why does this matter? Well, it might not, but it kind of just gives you an idea of how these pieces fit together. And we think that millions and trillions, they're both huge numbers, and they are. But you can see how a trillion is so much bigger, because you can take a million, millions, and put them together to get a trillion. So it really just emphasizes how much bigger a trillion is compared to a million. Because for us, especially if you think about money, you're never going to make $1 million. Well, I shouldn't say you're never. I'm never going to make $1 million. So it's hard to think about really a difference between million and trillion. Okay, let's go to number 7. Counting to 1 billion. How long would it take you to count to 1 billion if it takes you 1 second to count each number? Now, the easy answer is 1 billion seconds. And that's legit, right? It's going to take you 1 billion seconds. But I can't comprehend how big that is. So if I say, well, there are 60 seconds in 1 minute, that right there makes my seconds go away and it'll put me in minutes. And I'm telling you right now, that's still a lot of minutes. So I'm also going to say, let's go, there are 60 minutes in 1 hour. And I'm going to go so far as to say, because that'll get rid of minutes, that's a lot of that. I'm going to go say 24 hours in 1 day. Now, at that point, I'm going to stop and I'm going to do some math. So I know that 1 billion is 1 with 9 zeros. If I take 1 billion, I'm going to start at 1 billion, divide by 60 because it's in the bottom, divide by 60 because it's in the bottom, and divide by 24. So this is 1 billion, divide by 60, divide by 60, divide by 24. That puts me in days. And mathematically, that gives me 11,574 days. That's a lot of days. So I'm going to go one step further and say there are 365 days in 1 year. That gets me out of days. So when I take 11,574 divided by 365, I end up with approximately 31.7 years. If you want to count to 1 billion at 1 second per number, it'll take you 31.7 years. And that's assuming that you can say 2,345,632 in 1 second. So you can know in actuality it would take you longer than 31.7 years. Longer than some of you have been alive, which is crazy. Number 8. According to some stats, around 1.35 million people were incarcerated in state prisons, 217,800 in federal prisons, and 744,500 in local jails. That approximates to be 2.2 million Americans. If it costs $25,000 to house each inmate for a year, approximately how much is spent on incarcerations. Now, we have this many total, 2.2 million. Each one costs $25,000. So it's going to cost us more than $2 million because each one of those Americans costs $25,000, which means we are going to multiply. Correct. 2.2 million times 25,000. So let's go to scientific notation to make this easier. Million means 6. 2.1234. 2.5 times 10 to the 4th. So when I multiply 2.2 times 2.5, I end up with 5.5 times 10 to the 6 plus 4 is 10. So when I go ahead and change this to standard form, right, I'm moving my decimal 10 places to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It costs us approximately $55 billion a year on inmates. That's a lot of dough, yo. Lots of dough. And number 9, the sun is dying. The sun is estimated to have only 5 billion years of life left. Should we be worried? Hopefully you say no, just looking at 5 billion years. But if we round the human lifetime to 100 years, how many human lifetimes does the sun have left? So we're going to take the sun, which is 5 billion, and we're going to divvy it up into human lifetimes. And as soon as you start splitting it up, you know you're dividing. So 5 billion divided by 100, because a lifetime is 100 years. Well, 5 billion, billion is 10 to the 9th. 100 is 1 times 10 to the 2nd. So when I divide this, 5 divided by 1 is 5. 9 minus 2 is 7. And if I go my decimal point 7 places to the right, 1, 2, 3, 4, 5, 6, 7, 50 million lifetimes. So assuming that you have a kid and each one of the kids lasts 100 years, 50 million of them can happen before the sun dies. So, I feel like we're in pretty good shape in terms of the sun. Number 10. The mass of the Earth is about 6 times 10 to the 21st metric tons, and the mass of the sun is about 1.998 times 10 to the 27th metric tons. Both of those numbers are so large, I can't comprehend them. About how many more is the mass of the sun compared to the mass of the Earth? Now, when you set this up and you're thinking about this, okay, this last sentence is what I want to look at. It says, how many, I'm missing a word. There should be the word time. How many times more, I can't believe I forgot a word. How many times? Time implies multiplication. So we're multiplying two things together. How many times more is? Is means equals. Is the mass of the sun compared to the Earth. So the Earth times some unknown value is going to equal the mass of the sun. Now, algebraically, which I know this class is not algebra, but just working with me here, we're trying to get this unknown value. So the opposite of multiplication is division. If I would divide both sides by the Earth divided by Earth, that's saying 4 divided by 4, right? It's just 1. So I would get this unknown value equals the sun divided by the Earth. So if I take the sun, 1.998 times 10 to the 27th, divided by the Earth, 6 times 10 to the 21st, now I can figure out how many times bigger. So I divide my numbers, and that gives me 0.333 times 10 to the 27 minus 21 is 6. So when I've moved my decimal 6 places to the right, 1, 2, 3, 4, 5, 6, the mass of the sun is 333,000 times bigger than the mass of the Earth. And it doesn't look like that when you look at those two numbers, but when you do the math, it is 333,000 times bigger. And the last one for this video. Tootsie.com states that 64 million Tootsie Rolls are produced each day. If they've been steadily producing this amount since the company moved to Chicago in 1968, how many Tootsie Rolls, spelled that wrong, have been produced in Chicago? Well, okay, we don't know exactly when in 1968. We're going to assume 2016 is over. Okay, we're going to do a little bit of estimating here. So if I say, okay, we're in 2016, they moved in 1968. That means they've been producing Tootsie Rolls in Chicago for 48 years. But they produce this many Tootsie Rolls per day. So 48 years, well, in 1 year, there's 365 days. So doing that conversion, we know we'd multiply 48 years times 365 days. That means they've been producing Tootsie Rolls for 17,520 days. Okay, each day they produce 64 million a day. So 64 million each day for 17,520 days. I put those together. I'm going to multiply 17,520 times 64 million. Okay, this is a big number. So if I would do 1.752 times 10 to the 4th times 6.4 times 10 to the 6th, right? Because million means 6. Now, when I put those together, 1.752 times 6.4 yields 11.2128 times 10 to the... Oh, Becky made a mistake. Did you guys catch my mistake? Because I almost didn't. Million is 6. Move it one more. This needs to be a 7. 6.4 times 10 to the 7th, because million is 6, and I moved my decimal. Whew! Sleeping on the job. So I've got 11.2128 times 10 to the 7th. No, gosh dang it, I'm killing myself here. 7 plus 4 is 11. Whew! Okay, now, if you look at this, I'm going to go ahead and say, well, let's change this to scientific notation. 1.12128 times 10 to the 12th. 11 is bigger than 10, so you would move it up by 1. And when I see 10 to the 12th, that's trillion. So 1.12 trillion Tootsie Rolls, I rounded, have been produced in Chicago since 1968. Now, you could have just multiplied 64 million times 17,520. You would have still gotten the 1.12 trillion. So there's a couple different ways you could multiply that. I'm just trying to use scientific notation since that is the title of the section. And that, my friends, is that.